Hello there, and welcome to the Sleepy Library. It's lovely to have you here. Before we begin tonight's journey through the cosmos, I'd love to know, where in the world are you listening from? A quiet bedroom with the curtains drawn, a peaceful train ride home, a cozy couch beneath a warm blanket. Wherever you are, I hope you're comfortable, safe, and ready to gently float away into thought. If you enjoy these relaxing explorations of the universe and would like to hear more, a like and subscribe really helps this sleepy little channel continue its voyage. And to those of you already subscribed, thank you. Truly, your support means more than you know. Now, I'll try not to make tonight's topic so interesting that it keeps you wide awake. But, if it does, at least you'll have a better understanding of just how strange and wonderful the universe truly is. A small price to pay for a restless night. So, let's begin, shall we? Tonight, we're going to drift beyond our own solar system, past the familiar planets we learned about in school, beyond Jupiter's stripes and Saturn's rings, into a realm where planets behave in ways that seem almost impossible. We're going to visit worlds where glass rains sideways in screaming winds, where oceans are made of molten rock, where planets wander alone in the cosmic darkness without any star to call home. These are the strange planets outside our solar system, the exoplanets, and their stories are both beautiful and quietly unsettling in the best possible way. The universe, it turns out, has quite the imagination, far more creative than we ever expected. And as we explore these distant worlds together, one peculiar planet at a time, you'll see that our own Earth, with its gentle blue skies and stable orbit, is actually quite unusual. Perhaps even a little boring compared to what's out there. But don't worry, we'll move slowly, softly, from one world to the next, with plenty of time to let each strange detail settle in your mind like snow falling on a quiet winter evening. So, tuck yourself in, close your eyes if you'd like, and let's embark on this gentle voyage to the strangest corners of our galaxy. When we think of rain, we think of water. Soft drops falling from grey clouds, pattering on windows, filling puddles on sidewalks. Rain is gentle, familiar, soothing even. But on a planet called HD 189733b, rain means something entirely different. Something violent and impossible and strangely beautiful. This planet, located about 65 light-years from Earth, doesn't have clouds of water vapor. It has clouds of glass. Tiny particles of silicate, the same material that makes up sand on Earth, suspended high in the atmosphere. And when conditions are just right, these particles condense and fall, not as gentle drops, but as molten shards of glass, heated to temperatures that would instantly vaporize any living thing. But here's where it gets truly strange. This glass doesn't fall straight down like rain on Earth. HD 189733b is what astronomers call a hot Jupiter, a massive gas giant that orbits incredibly close to its star, so close that it completes a full orbit in just over 2 days. The planet is tidally locked, meaning one side always faces its star, while the other side faces away into eternal darkness, just like our moon always shows the same face to Earth. This creates enormous temperature differences between the day side and the night side, differences of more than 1,000 degrees, And these temperature differences create winds. Not gentle breezes, not even hurricane-force winds. Winds that scream across the planet's surface at speeds reaching 5,000 miles per hour, 7 times the speed of sound. Imagine standing on this world, if such a thing were possible. The sky above you would be a deep, rich blue, almost like Earth's sky on a clear summer day. It's one of the few exoplanets whose color we've been able to measure, and that cobalt blue is hauntingly familiar. For a moment, you might think you're looking at something peaceful. But that blue doesn't come from scattered sunlight in a breathable atmosphere. It comes from those clouds laced with glass particles, from an atmosphere so hot it would melt lead, from temperatures hovering around 1,700 degrees Fahrenheit. The light scatters through the silicate haze, creating that deceptively beautiful blue, while beneath it, the planet churns with violence. And then there's the rain. Driven by those impossible winds, the molten glass doesn't fall vertically. It flies horizontally, whipping across the planet in endless storms. Imagine millions of tiny glass shards, each one heated to temperatures that glow dull red, all of them racing through the atmosphere faster than any bullet, faster than any tornado, carried by winds that would tear apart anything in their path. It's not rain in any way we would recognize. It's a weapon, a storm of cutting, burning fragments that never stops, never rests, circling the planet endlessly as it races around its star. Scientists studying HD 189733b have found that the planet's atmosphere is also surprisingly rich in other compounds. There's sodium and potassium vapor, metals that have been boiled off the planet's interior by the intense heat. There's hydrogen sulfide, the same chemical that gives rotten eggs their smell, though of course, no one would be alive long enough on this world to notice the odor. The James Webb Space Telescope recently studied this planet's atmosphere in detail, and what researchers found was both fascinating and sobering. The atmosphere is being slowly stripped away by the star's radiation, bleeding into space at a rate of hundreds of millions of pounds per second. This planet is slowly evaporating, losing pieces of itself to the void, while still managing to maintain those violent glass storms. It's a world in transition, caught between existence and dissolution, beautiful and terrible at the same time. When you look at HD 189733b through a telescope, you see a small blue dot, peaceful and serene. You'd never guess the violence hidden in that calm appearance. And perhaps that's one of the universe's gentle lessons, that beauty and terror are not opposites. They can exist together, intertwined, each one making the other more striking by contrast. As we drift away from the glass rain planet, let's journey to another world that pushes the boundaries of what seems possible. A planet where the ground itself flows and glows, where one side is bathed in eternal fire, while the other freezes in endless darkness. This world is called 55 Cancri E, though it has also been given the more romantic name Janssen, after a Dutch astronomer. It sits about 40 light-years from Earth, in the constellation Cancer, and it is a planet of two faces, forever locked in a strange and beautiful struggle between extremes. 55 Cancri E is what scientists call a super-Earth, meaning it's larger than our planet, but smaller than the gas giants like Jupiter or Saturn. It has about twice Earth's width and 8 times its mass, making it dense and rocky, more solid than airy. But unlike Earth, this planet orbits its star at a distance so small, it completes a full orbit in just 18 hours. 18 hours for a full year. It circles its sun closer than Mercury circles ours, so close that the star's gravity has locked the planet's rotation. One hemisphere, the day side, faces the star constantly, baking under its relentless light and heat. The other hemisphere, the night side, never sees the star at all, left to cool in perpetual shadow. And this creates one of the most dramatic contrasts in the known universe. On the day side, temperatures soar to around 4,400 degrees Fahrenheit, hot enough to melt iron, hot enough to vaporize rock. And that's exactly what happens. The surface of 55 Cancri E on its day side is thought to be covered by a global ocean of lava, molten rock flowing and churning like water on Earth. Picture it if you can, a sea of glowing orange and red, viscous and thick, with waves of molten stone rolling slowly across the landscape. The heat is so intense that some of that lava likely vaporizes, creating clouds of rocky vapor that drift through the atmosphere like fog, only to rain back down as tiny droplets of liquid stone. Recent observations from the James Webb Space Telescope have revealed something unexpected about this lava world. It has an atmosphere, but not one made of familiar gases like oxygen or nitrogen. Instead, the air around 55 Cancri E seems to be rich in carbon dioxide or carbon monoxide, heavy gases that bubble up constantly from the churning lava ocean below. This is called a secondary atmosphere, meaning it's not the original atmosphere the planet formed with. That one was likely stripped away long ago by the star's intense radiation. Instead, this new atmosphere is continuously replenished by the planet itself, by gases escaping from the molten rock, by the endless cycle of vaporization and condensation. The lava ocean breathes, in a way, exhaling gases into the sky above it, creating weather patterns unlike anything we've ever seen. And what about the night side? Turn away from the star, cross that boundary from day to night, and the world transforms. Temperatures drop dramatically, falling to around 2,000 degrees Fahrenheit. Still unbearably hot by our standards, but cool enough that the lava solidifies. The night side of 55 Cancri E is thought to be covered in dark, hardened rock, a frozen crust that never sees sunlight, never feels warmth except what little heat conducts through from the day side. It's a landscape of stillness, of quiet darkness, while just over the horizon, the lava ocean rages on. Between these two extremes, scientists believe there may be a narrow twilight zone, a region where the temperature is just right for some interesting chemistry to occur. Not life, of course. The conditions are far too extreme for that. But perhaps strange minerals forming, perhaps crystals growing in the cooler margins, perhaps clouds of vaporized rock drifting between solid and liquid states. There was once speculation, wild and romantic speculation, that planets like 55 Cancri E might be made of diamond. The idea came from calculations suggesting that carbon-rich planets could, under certain conditions, form diamond interiors rather than the silicate composition we see on Earth. The media loved this idea. A diamond planet, glittering in the darkness, a world made of gemstones. But more recent research has cast doubt on this theory. While 55 Cancri E does seem to have an unusual amount of carbon in its atmosphere, the idea of a solid diamond core is probably more science fiction than science fact. Still, there may be other precious minerals on this world. Sapphire-like formations could exist in its crust, created by the extreme temperatures and pressures. The landscape might shimmer with crystalline structures, with minerals we can barely imagine, with colors we've never seen. Even without being made of diamond, this planet sparkles in its own right. Its lava ocean glowing like embers, its rocky surface reflecting the distant star in ways that make the whole world glow faintly red even from the night side. 55 Cancri E reminds us that planets don't have to be habitable to be beautiful. That even in the most extreme environments, the universe finds ways to create something that inspires wonder. And as we move on to our next destination, carry that image with you. A world split between fire and shadow, between motion and stillness, glowing softly in the darkness of space, like a distant ember that refuses to go out. Let's drift now to a stranger kind of planet, one that challenges our very definition of what a planet is supposed to be. These are the wanderers, the lost ones, the rogue planets. Worlds that have no star to orbit, no sun to warm them, no central anchor. They float alone through the vast emptiness of interstellar space, silent and cold, traveling through the darkness like cosmic orphans. For most of human history, we assumed that planets needed stars, that they formed in the swirling disks around young suns and stayed there, held by gravity in neat orbits. But in the last few decades, astronomers have discovered something surprising. There are planets out there, maybe billions of them, that have broken free from their stars entirely. Or perhaps they never had a star to begin with. These rogue planets, also called free-floating planets, drift through the galaxy on their own trajectories, following paths determined by ancient gravitational encounters, by close calls with other stars, by the chaotic early days of planetary system formation. Some of them were likely ejected from their home systems by the gravitational influence of larger planets. Imagine a young solar system, still settling into its final configuration, with massive gas giants jostling for position. One smaller planet gets caught in the wrong place at the wrong time, and like a marble struck by a much heavier ball, it's flung outward, faster and faster, until it escapes the star's gravity entirely and tumbles out into the void. Other rogue planets may have formed differently, not around a star at all, but directly from the collapse of clouds of gas and dust in interstellar space, forming like stars but too small to ignite nuclear fusion. These would be the lowest mass objects that form like stars, technically planets by mass, but orphans by birth. Either way, the result is the same. A world alone in the darkness, with no sunrise to mark the passing of days, no seasons, no warmth from a nearby sun. These planets are cold, unimaginably cold. Without a star to provide heat, rogue planets cool over time, radiating away their internal warmth into the endless night. Temperatures on their surfaces likely hover just a few degrees above absolute zero, the coldest possible temperature in the universe. Any atmosphere they once had would freeze and fall as snow, coating the surface in layers of frozen gas. Water, if it exists, would be solid ice, hard as rock. Carbon dioxide would solidify into dry ice. Even the air itself, if there is air, would turn to frost. Recent surveys have tried to estimate just how many of these lonely worlds exist in our galaxy. The numbers are staggering. One study suggests there may be as many as 2 trillion rogue planets in the Milky Way, outnumbering stars by a ratio of about 2 to 1. Another study, more conservative, still estimates hundreds of billions of these wanderers. Either way, the implication is clear. Rogue planets are common, perhaps even more common than planets orbiting stars. Our own solar system may have ejected planets in its distant past, worlds that now drift somewhere out there in the galactic night, carrying with them the memory of a sun they once knew. And here's something even stranger. Some of these rogue planets might not be entirely lifeless. It sounds absurd at first. How could life exist on a world without a star? Life needs energy, and on Earth, nearly all of that energy comes from the sun. But scientists have speculated about a few scenarios where rogue planets could, at least in theory, support some form of life. If a rogue planet retained a thick hydrogen atmosphere from its formation, that atmosphere could act like a blanket, trapping heat from the planet's own radioactive core. This internal heat, generated by the slow process of radioactive elements undergoing transformation, could keep the planet's surface warm enough for liquid water to exist even without a sun. It would be a dim world, lit only by the faint glow of volcanic activity or bioluminescent organisms if life did evolve there. But it wouldn't be frozen solid. Another possibility involves moons. If a rogue planet managed to keep one or more large moons in orbit around it, those moons could experience tidal heating, just like Jupiter's moon Io or Saturn's moon Enceladus. The planet's gravity would squeeze and stretch the moons, generating heat through friction, potentially creating subsurface oceans beneath icy crusts. And in those hidden oceans, in the darkness beneath the ice, life might find a way. We've found life in extreme environments on Earth, in deep ocean vents where no sunlight reaches, in acidic hot springs, in frozen lakes beneath Antarctica. Life, it seems, is resourceful. And if it can survive in those places, who's to say it couldn't survive on a rogue planet or its moons? Of course, these are speculations, thought experiments more than predictions. But they remind us that the universe is full of possibilities we haven't imagined yet. That even in the coldest, darkest corners of space, there might be worlds with stories of their own. Rogue planets also challenge our sense of cosmic order. We like to think of solar systems as stable, predictable places, where planets follow neat orbits like clockwork. But the existence of rogue planets tells us that planetary systems are messy, chaotic, violent in their youth. That many worlds don't survive the early tumult. That our own solar system's stability is perhaps a bit of good luck, a configuration that happened to work out, while other systems lost planets to the void. And somewhere out there, in the darkness between the stars, those lost worlds continue their silent journeys. They pass through clouds of gas and dust. They drift by distant stars without slowing. They travel for millions, perhaps billions of years, seeing things no telescope will ever capture, bearing witness to the slow turning of the galaxy. They are the loneliest objects we know of, and yet there's something oddly peaceful about them, a kind of quiet dignity in their solitude. Let's leave the cold wanderers behind now, and travel to a world that offers a very different kind of strangeness. A planet with two suns. This isn't science fiction, it's real, and it's beautiful, in a way that feels almost too perfect to be true. The planet's name is Kepler-16b, and it orbits not one star, but two stars that orbit each other. It's what astronomers call a circumbinary planet, a world where you would see two suns in the sky, rising and setting together, casting double shadows on the ground. When Kepler-16b was discovered in 2011, it immediately captured people's imaginations. It reminded everyone of Tatooine, the desert planet from Star Wars, where Luke Skywalker watches two suns set over the horizon. That iconic scene, once thought to be pure fantasy, turned out to be scientifically plausible. And now we know that planets like Kepler-16b exist, and they're not even that rare. Kepler-16b sits about 200 light-years from Earth, in the constellation Cygnus. It orbits two stars, one about 2/3 the mass of our Sun, and the other much smaller, only about 1/5 the Sun's mass. These two stars orbit each other closely, completing a full circuit every 41 days. And Kepler-16b orbits around both of them, taking 229 days to complete one wide loop. It's a bit like a planet dancing around a binary waltz, following the lead of two partners who are themselves spinning together. The stars in this system are cooler and dimmer than our Sun, which means that despite Kepler-16b's relatively close orbit, the planet is cold. Its surface temperature hovers around -100 to -150 degrees Fahrenheit. It's a gas giant, similar in size and mass to Saturn, with no solid surface to stand on. So, while it's a real-life Tatooine in terms of having two suns, it's not a world where anyone could watch that double sunset with their own eyes. Still, if you could somehow float in its upper atmosphere, protected from the cold and the lack of oxygen, the view would be breathtaking. Imagine looking up and seeing two suns in the sky, one larger and brighter, glowing orange-red, the other smaller and dimmer, a deep red ember beside its companion. They would move together across the sky, rising and setting as a pair, their light mingling to create colors and shadows unlike anything we see on Earth. During the day, the landscape, if there were a landscape, would be bathed in a strange warm light, tinged with orange and red hues. And at sunset, you'd watch both suns dip below the horizon, one after the other, the larger one first, followed by its smaller sibling, until the sky dimmed to darkness. Your shadow wouldn't be a single dark line. It would be doubled, or even tripled at certain times, each sun casting its own shadow in slightly different directions. And at midday, those shadows might overlap, or they might diverge, creating patterns that shift and change as the stars move across the sky. It would be disorienting at first, but also mesmerizing. A constant reminder that you're standing on a world orbiting two stars, not one. What's particularly fascinating about Kepler-16b is how precise our measurements of it are. Because the planet transits in front of both stars from our point of view, meaning it passes between us and the stars, blocking a tiny bit of their light, astronomers were able to calculate the planet's size, mass, and orbit with incredible accuracy. In fact, when it was first discovered, scientists claimed it was the best measured planet outside our solar system. We know its radius to within a fraction of a percent, better than we know the radii of some planets in our own solar system. This level of precision is rare and valuable, giving astronomers a clear picture of what circumbinary planets are like. And it turns out, they're not as unusual as we once thought. Since the discovery of Kepler-16b, astronomers have found several other planets orbiting binary stars. Some of these systems have multiple planets, all of them orbiting the binary pair in wide, stable orbits. These findings suggest that circumbinary planets are common, that planetary formation can occur even in the complex gravitational environment of a binary star system. Theorists had worried that the gravitational tug-of-war between two stars would prevent planets from forming, or would destabilize their orbits, flinging them out into space. But nature, it seems, is more adaptable than we gave it credit for. Planets can form in these systems, and they can survive there for billions of years, orbiting in regions where the gravitational forces balance out just right. There's also the tantalizing possibility of habitable worlds in circumbinary systems. Kepler-16b itself is too cold and too gaseous to support life. But that doesn't mean all circumbinary planets are. If a planet orbited farther out, in the habitable zone, where temperatures are just right for liquid water, it could, in theory, be a place where life might arise. Imagine an Earth-like world circling two suns, with seasons determined not just by the planet's tilt, but by the changing distances and positions of both stars. It would be a world of complex rhythms, where the length of days and the intensity of sunlight varied in intricate patterns. Life on such a world would need to adapt to those patterns, but evolution is remarkably good at adapting to strange environments. For now, Kepler-16b stands as a beautiful proof of concept. A reminder that the universe contains wonders we once thought belonged only to stories. That you can have a planet with two suns, and that it's not just possible, it's real. And somewhere out there, 200 light-years away, those two stars continue their ancient dance, with a cold gas giant silently circling them both, a world of double sunsets that no one will ever see. As we drift onward, let's visit a planet that seems to be in the process of vanishing before our very eyes. This world is called WASP-12b, and it is a planet on borrowed time. It orbits so close to its star, so dangerously close, that the star's gravity is literally tearing the planet apart, stripping away its atmosphere layer by layer, pulling the planet's very substance into space. It's a slow process, happening over millions of years, but it's happening nonetheless. And one day, perhaps 3 million years from now, WASP-12b will be gone entirely, consumed by the very star it orbits. WASP-12b is another hot Jupiter, a gas giant that has somehow ended up orbiting just 3 million miles from its star, about 13 times closer than Mercury orbits the Sun. At that distance, the planet completes a full orbit in just over 1 Earth day. 1 day to circle its entire star, and at that distance, the star's gravitational pull is immense, powerful enough to distort the planet's shape. Instead of being a sphere, WASP-12b has been stretched into an oval, like an egg. The side facing the star is pulled outward by tidal forces, creating a bulge, a swelling of gas and atmosphere that reaches toward the star like a hand stretching out. Scientists call this shape prolate, and it's one of the most extreme examples of tidal distortion we've ever observed. But the distortion is just the beginning. The real drama lies in what's happening to the planet's atmosphere. WASP-12b is so close to its star that temperatures on its day side reach around 4,000 degrees Fahrenheit. At those temperatures, the atmosphere becomes superheated, causing the gases to expand outward. And because the planet's gravity isn't strong enough to hold on to this expanding atmosphere, the gases escape into space. This process is called atmospheric escape, and it's happening to WASP-12b at a staggering rate. The planet is losing mass at about 1/10,000,000th of a Jupiter mass per year. That might sound like a tiny amount, but it adds up. Over the planet's lifetime, it has likely lost a significant fraction of its original mass, and it's still losing more every second. Roughly 200 million kilograms per second are being stripped away, flowing out into the space around the planet, forming a thin cloud of gas that spreads out in a wide halo. Some of that gas is pulled into the star itself, spiraling inward and eventually being absorbed. Some of it forms a ring or torus around the star, a diffuse cloud of hydrogen and heavier elements, creating a ghostly shroud around the entire system. Observations from the Hubble Space Telescope have actually detected this escaping atmosphere. Scientists observed the planet's transit across its star and noticed that the star's light was being absorbed by gases far beyond the planet's expected size. The planet's exosphere, the outermost layer of its atmosphere, has ballooned to nearly 3 times the radius of Jupiter, creating a vast, translucent envelope that extends far into space. It's as if the planet is surrounded by a bubble of its own dissolving substance, a reminder of what it once was, and a preview of what it's lived becoming. And there's more. WASP-12b's orbit is not perfectly circular. It's slightly elliptical, meaning the distance between the planet and the star changes over the course of the orbit. This variation causes the tidal forces to fluctuate, generating heat inside the planet through friction. That heat contributes to the planet's inflation, causing it to swell even larger than it would otherwise be, which in turn makes it easier for the atmosphere to escape. It's a vicious cycle, a feedback loop that accelerates the planet's demise. But perhaps the strangest part of this story is that WASP-12b's orbit is decaying. It's not just losing its atmosphere, it's also spiraling inward, slowly but steadily, pulled by the same tidal forces that are ripping it apart. Scientists have measured the planet's orbital period over many years and found that it's getting shorter by about 30 milliseconds per year. That might sound insignificant, but it's a clear sign that the planet is falling into its star. At this rate, WASP-12b has only about 3 million years left before it's consumed entirely. 3 million years sounds like a long time to us, but in cosmic terms, it's the blink of an eye. For a planet that's probably 2 billion years old, spending its last 3 million years in a death spiral is a brief and dramatic finale. And we're witnessing it right now, in real time, as the planet slowly fades away. Astronomers are fascinated by WASP-12b because it offers a rare glimpse into the end stages of a planet's life. Most planets we study are stable, orbiting at safe distances from their stars, with billions of years of existence ahead of them. But WASP-12b is different. It's a planet in transition, a world being unmade, and by studying it, we learn about the extreme limits of planetary survival. There's something oddly poetic about this doomed world. It reminds us that nothing in the universe is permanent, that even planets, massive and ancient as they are, can dissolve back into the cosmos from which they came. WASP-12b is returning to its star, giving back the material it borrowed billions of years ago, completing a cycle of formation and decay that's both beautiful and melancholy. And as we observe it from across the light years, we're watching a quiet tragedy unfold, a planet's final act played out against the backdrop of an indifferent universe. Let's move to a planet that defies our expectations in a different way. This is a world where water exists in a form that seems impossible, where ice can remain solid even at temperatures hot enough to boil metal. It's called a super-Earth, and it goes by the designation GJ-436b. This planet challenges our understanding of how matter behaves under extreme conditions, showing us that the universe has tricks up its sleeve that seem to break the rules of common sense. GJ-436b is about the size of Neptune, orbiting a red dwarf star roughly 30 light-years from Earth. It's a planet that shouldn't exist, or at least it shouldn't be where it is. It sits very close to its star, close enough that surface temperatures reach around 800 degrees Fahrenheit. At those temperatures, any water on the surface should be a gas, a cloud of steam that floats away into space. But something strange is happening on GJ-436b. The planet's atmosphere seems to contain water, not as a gas, not as liquid, but as a form of hot ice. This isn't the ice you find in your freezer. It's not cold. It's not even cool. It's ice that exists because of extreme pressure, not low temperature. Deep inside planets, the pressure from all the layers above can be so intense that water molecules are crushed together into a solid state, even if the temperature is hundreds or thousands of degrees. This exotic form of water ice is called Ice 7 or Ice 10, depending on the exact structure, and it's one of several high-pressure phases of ice that scientists have studied in laboratories. On Earth, we're familiar with regular ice, the kind that forms when water freezes at 32 degrees Fahrenheit. But that's just one phase of ice. Under different conditions of pressure and temperature, water can form at least 18 different types of ice, each with a unique crystalline structure. Some of these phases require pressures millions of times higher than the pressure at Earth's surface, the kind of pressures you'd find deep inside giant planets or in the cores of icy moons. And GJ436b seems to have conditions where one of these exotic ice phases can exist despite the planet's high temperatures. The water is squeezed so tightly by the planet's gravity that it can't melt or evaporate, even though it's burning hot. It's frozen not by cold, but by pressure. Imagine holding a piece of this ice in your hand, if such a thing were possible. It would be hot to the touch, possibly glowing faintly, but it would be solid, unyielding, a block of frozen water that refuses to melt no matter how much heat you apply. It's a contradiction, a paradox, and yet it's real. The discovery of hot ice on GJ436b and similar planets has profound implications for our understanding of planetary interiors. Many of the exoplanets we've discovered are super-Earths or mini-Neptunes, worlds larger than Earth but smaller than Neptune, and we're still trying to figure out what they're made of. Some might be rocky, with thick atmospheres. Others might be water worlds covered in deep oceans. And some, like GJ436b, might have interiors dominated by these strange, high-pressure ices, creating worlds that are neither rocky nor gaseous, but something in between. These planets could have layered structures, with a core of rock or metal, surrounded by a thick mantle of hot ice, and capped by a dense atmosphere of hydrogen and helium. It's a very different architecture from what we see in our solar system, and it suggests that the diversity of planets in the universe is even greater than we imagined. GJ436b also challenges the idea that planets in tight orbits should quickly lose their atmospheres. Despite being blasted by intense radiation from its star, despite being so close that it completes an orbit in less than 3 days, this planet has managed to hold onto a substantial atmosphere, one thick enough to maintain these exotic conditions. There's something quietly fascinating about the idea of hot ice. It reminds us that our everyday experience of matter, of how things behave at the temperatures and pressures we're used to, is just one tiny slice of what's possible. That water, something so familiar and essential to life on Earth, can take on forms that seem alien and impossible. That the rules we think we know are just approximations, useful within a narrow range of conditions, but incomplete when we venture into the extremes. GJ436b is one of many worlds where those extremes are the norm, where the impossible becomes routine, where matter is squeezed and heated and transformed into states that we can barely comprehend. And as we continue to study these planets, we're learning not just about them, but about the fundamental nature of matter itself. What happens when you compress water beyond its breaking point? What new phases emerge? What properties do they have? These are questions with answers that could reshape our understanding of chemistry and physics, all thanks to a planet orbiting a distant red dwarf star, a world of hot ice that shouldn't exist, but does. Let's continue our journey to a planet that embodies silence. Absolute, perfect silence. This is a world called Kepler 78b, and it's a place where there is no wind, no weather, no atmosphere to carry sound. If you could somehow stand on its surface, which you couldn't, you would experience a silence so profound it would be unsettling. Every footstep, every breath, every sound you made would vanish immediately, absorbed into the barren rock beneath you, with nothing to echo, nothing to carry the vibrations. It would be the quietest place in the universe. Kepler 78b is a small planet, about the same size as Earth, but it orbits its star incredibly close, so close that it completes a full orbit in just 8.5 hours. 8.5 hours for a year. At that distance, the planet is subjected to intense heat and radiation, heating its surface to around 3,000 degrees Fahrenheit. That's hot enough to melt rock. Hot enough that the surface is likely a sea of molten lava, glowing red and orange like the inside of a furnace. But here's the thing. At those temperatures, any atmosphere the planet might once have had would have been stripped away long ago. There's no air, no clouds, no gases at all. Just rock and metal, baking under the relentless glare of the star. Without an atmosphere, sound cannot travel. Sound is a wave that propagates through matter, whether that's air, water, or solid rock. But the thin, molten surface of Kepler-78b offers no medium for sound waves to propagate through the vacuum of space around it. If you could place a speaker on this planet and turn it on, it would produce no sound. The vibrations would move through the speaker itself, but they wouldn't travel beyond it. There would be no air to push, no molecules to jostle, no way for the wave to move from one place to another. It would be like shouting into a void, except even worse, because the void wouldn't even acknowledge your shout. The silence wouldn't be eerie or ominous. It would just be absolute. Of course, there's another reason you couldn't hear anything on Kepler-78b, and that's because you'd be instantly vaporized by the heat. But setting that aside, the silence is worth contemplating. It's a reminder that the universe is mostly silent. Space itself is a vacuum, and sound cannot travel through a vacuum. When we watch movies set in space, we hear explosions and engines roaring and lasers zapping. But in reality, all of those events would be utterly silent. The only sounds in space are those that propagate through solid objects or through the plasma of stars. And even those sounds are nothing like what we'd hear on Earth. Kepler-78b is an extreme example of this cosmic silence. It's a planet with nothing to say, no winds to howl, no waves to crash, no tectonic plates to grind. Just a molten surface slowly rotating under a nearby star, glowing and radiating heat into the void. And yet, there's something oddly peaceful about that image. A world without noise, without disturbance, where the only motion is the slow churn of lava and the steady orbit around its star. Scientists are interested in Kepler-78b for a different reason, though. Despite its proximity to its star, the planet's density suggests it's made of rock and iron, much like Earth. That's unusual for a planet so close to its star, because most planets at that distance are gas giants, or have lost so much mass to evaporation that their composition is unclear. But Kepler-78b seems to be a genuine rocky planet, one that somehow survived the intense environment it's trapped in. How did it get there? Did it form close to the star, or did it migrate inward over time? And why hasn't it been completely destroyed by the star's heat and radiation? These are questions that astronomers are still trying to answer. Kepler-78b is a puzzle, a planet that shouldn't exist according to some models of planetary formation, and yet clearly does. And by studying it, scientists hope to learn more about the limits of planetary survival, about what conditions allow rocky planets to endure even in the harshest environments. For us, though, Kepler-78b serves as a meditation on silence, on the idea that there are places in the universe where sound simply doesn't exist, where the only communication is the silent exchange of light and heat, where the only language is gravity and radiation. It's a humbling thought, and also a calming one, that somewhere out there, there's a planet where everything is still, where the chaos and noise of the universe fade away, leaving only the quiet glow of molten rock and the endless, empty silence of space. Let's drift now to a planet that occupies the other end of the spectrum, a world that doesn't glow or howl, but simply doesn't reflect. This is TRES 2b, and it holds the title of the darkest planet ever discovered. If you could somehow see it up close, it would appear as a shadow, a black hole against the stars, absorbing light like a cosmic sponge and reflecting almost nothing back. TRES 2b is located about 750 light-years from Earth in the constellation Draco. It's a gas giant, similar in size to Jupiter, and it orbits its star at a distance close enough to make it a hot Jupiter, with surface temperatures exceeding 2,700 degrees Fahrenheit. But what makes this planet truly unique is its albedo, the measure of how much light it reflects. Most planets reflect at least some of the light that hits them. Earth reflects about 37%, giving it a bright appearance from space. Jupiter reflects about 52%, thanks to its thick clouds of ammonia and other bright compounds. Even our Moon, which looks grey and dull, reflects about 12% of the sunlight that strikes it. But TRES 2b reflects less than 1%. In the best measurements, its albedo is around 0.04%, meaning it absorbs 99.96% of the light that reaches it. That makes it darker than coal, darker than black acrylic paint, darker than almost any substance we know of on Earth. It's the blackest planet in the known universe. Why is TRES 2b so dark? Scientists aren't entirely sure, but they have a few theories. One possibility is the planet's atmosphere. At the extreme temperatures found on TRES 2b, any reflective clouds, like those on Jupiter, would evaporate or break down. Instead, the atmosphere is likely filled with chemicals that absorb light rather than reflect it. Vaporized sodium and potassium, for example, are known to absorb visible light across a broad range of wavelengths. Gaseous titanium oxide is another candidate, a compound that would turn the atmosphere into a kind of chemical sponge, soaking up light and converting it into heat. There may also be hazes of complex organic molecules, similar to those found in Titan's atmosphere, that contribute to the planet's darkness. Another factor is the planet's temperature. Because TRES 2b is so hot, it emits its own thermal radiation, glowing faintly like a piece of metal heated in a forge. This glow is mostly in the infrared, invisible to our eyes, but it's there, a dull red radiance that adds a slight brightness to the planet, despite its refusal to reflect light. If you could see TRES 2b with infrared vision, it would appear as a dim ember, warm and glowing. But in visible light, it would be nearly invisible, a dark sphere outlined only by the faint light of the stars behind it. The discovery of TRES 2b's extreme darkness came from observations by the Kepler Space Telescope, which measured tiny changes in the planet's brightness as it orbited its star. As the planet moved from in front of the star to behind it, the amount of light detected changed, and by analyzing those changes, scientists could calculate how much light the planet was reflecting. The answer was almost none. This finding was surprising and a bit unsettling. It suggested that hot Jupiter planets, which astronomers had been studying for years, could be far darker than anyone expected. Most models of these planets assumed they would reflect at least a few % of the light that hit them. But TRES 2b showed that the reality could be very different. There's something almost spooky about a planet that's darker than coal. It feels wrong, somehow, like a glitch in the universe. We're used to planets being bright, colorful objects, or at least reflective enough to see. But TRES 2b breaks that expectation. It's a reminder that planets can have personalities, if you will, that range from the brilliant and shiny to the brooding and shadowy. And TRES 2b is definitely on the shadowy end of that spectrum. Despite its darkness, TRES 2b is not invisible. Its high temperature means it radiates enough heat to be detected with infrared telescopes, and its size means it blocks a noticeable amount of light when it transits in front of its star. But if you could somehow teleport to the planet's location and look at it with your own eyes, you'd see very little. A faint outline perhaps, a darker patch against the already dark sky, with just the barest hint of red glow if you looked closely. It would be like looking at a coal in a dying fire, barely visible but unmistakably there. TRES 2b challenges our assumptions about what planets should look like. It's a world of shadows, a place where light goes to disappear. And in its darkness, there's a strange kind of beauty. A reminder that the universe doesn't always follow our expectations, that sometimes the most interesting things are the ones we can barely see. And as we move forward on our journey, carry that thought with you. That darkness, like silence, has its own kind of presence. That absence can be as powerful as abundance. That even the blackest planet still has a story to tell, if we're willing to listen. Now let's consider what all these strange worlds might mean for us, for Earth, for the possibility of life elsewhere in the universe. Throughout this journey, we visited planets of glass rain and molten rock, of double suns and endless darkness, of hot ice and cosmic silence. And one thing becomes clear as we explore these worlds. Our Earth is strange too, in its own way. Not because it's extreme, but because it's so perfectly balanced. Earth orbits at just the right distance from the Sun, not too close, not too far, in what astronomers call the habitable zone or the Goldilocks zone. We have liquid water, a stable atmosphere, a protective magnetic field, and a climate that, while variable, has remained within a range that allows life to thrive for billions of years. When you compare Earth to the planets we visited tonight, you realize how rare this combination is. How many things had to go right for our planet to become the vibrant, living world it is today? And yet, as we discover more exoplanets, we're also finding that Earth-like planets might not be as rare as we once thought. There are billions of stars in our galaxy, and most of them have planets. Some of those planets orbit in the habitable zones of their stars, where temperatures are right for liquid water. Some of those planets are rocky, like Earth, rather than gaseous, like Jupiter. And while we haven't yet found a perfect twin of Earth, we found planets that come close. Super-Earths that orbit red dwarf stars. Worlds that might have oceans and continents and atmospheres that could support life. These discoveries are still tentative, based on indirect measurements and careful calculations. We can't yet see these planets in detail, can't study their surfaces or sample their atmospheres. But every year, our technology improves. The James Webb Space Telescope, launched recently, is already revealing new details about exoplanet atmospheres, detecting molecules like carbon dioxide, methane, and water vapor. Future missions will go even further, looking for signs of oxygen, ozone, or other chemicals that might indicate the presence of life. And then there's the question of what life on these worlds might look like. If life exists on a rogue planet, drifting in the cold darkness, it would need to survive without sunlight, drawing energy from geothermal heat or chemical reactions. If life exists on a planet with two suns, it would need to adapt to complex patterns of day and night, to varying intensities of radiation. If life exists on a tidally locked world, with one side in eternal day and the other in eternal night, it would need to thrive in extreme environments, perhaps clinging to the narrow twilight zone between the two extremes. Life on Earth has shown us just how adaptable and resilient it can be. We've found organisms living in boiling hot springs, in acidic lakes, in frozen Antarctic ice, in the deep ocean where no sunlight reaches, in radioactive waste, in the driest deserts. If life can survive all those environments on Earth, perhaps it can survive on some of these strange exoplanets too. Perhaps there are bacteria floating in the clouds of a hot Jupiter, thriving in the cooler upper layers where conditions are less extreme. Perhaps there are ecosystems on rogue planet moons, hidden beneath kilometers of ice, warmed by tidal heating. The universe, we're learning, is full of possibilities. And while the planets we've explored tonight are too extreme for life as we know it, they're not the only planets out there. For every glass rain world or lava ocean planet, there might be dozens of quieter, calmer worlds where conditions are just right. Worlds where water flows in rivers, where atmospheres are breathable, where the days and nights follow familiar rhythms. We just haven't found them all yet. And in a way, that's the beauty of it. We're still at the beginning of this grand exploration. We've only scratched the surface of what's out there. Every new discovery, every strange planet, every unexpected finding adds another piece to the puzzle. And slowly, gradually, we're building a picture of the universe that's richer and more diverse than anyone imagined. One day, perhaps not too far in the future, we might find a planet that truly is Earth-like. A world with blue skies and green forests, with oceans and mountains, with seasons and weather patterns we can understand. And when we do, it will change everything. It will show us that our home isn't unique, that life's potential isn't limited to one small blue dot. That the universe, vast and strange as it is, might be filled with worlds like ours, each one a stage for its own story, its own evolution, its own quiet dramas playing out under distant stars. For now, though, we're left with these strange planets, with glass rain and lava oceans, with rogue wanderers and double sunsets, with silence and darkness and hot ice. And there's something comforting in their strangeness. They remind us that we don't have all the answers yet, that the universe still has secrets to reveal, that there's still mystery and wonder waiting for us out there, if we're brave enough to look for it. Before we bring our journey to a close, let's spend a little more time with each of these remarkable worlds, letting the details settle in, allowing ourselves to truly appreciate the strangeness and beauty they represent. Because each planet we've visited tonight has its own personality, its own unique combination of features that make it unlike any other world we know. And in taking the time to understand them more deeply, we come to appreciate not just how strange they are, but how they fit into the larger story of planetary formation, evolution, and the endless creativity of the cosmos. Think back to HD 189733b, that planet of sideways glass rain. What must it be like for matter to exist in such extreme conditions? The silicate particles in the atmosphere are the same basic material that makes up beach sand on Earth. But here, they're vaporized, suspended in clouds, condensed into droplets, and then hurled across the planet at hypersonic speeds. The very molecules are experiencing temperatures and pressures that would seem impossible to us. And yet, the planet persists. It doesn't simply fly apart. Its gravity holds it together, even as its star's radiation tries to strip it away. There's a balance there, a precarious one, but a balance nonetheless. The planet is locked in a constant struggle between cohesion and dissolution. And for now, cohesion is winning, though that may not always be true. The color of HD 189733b, that deep blue, is particularly haunting. Blue is a color we associate with peace, with clear skies, with calm oceans. But on this world, blue means danger. It means clouds laced with glass, an atmosphere so hostile that nothing could survive there for even a fraction of a second. It's a reminder that appearances can be deceiving, that beauty and violence can coexist, that the universe doesn't care about our associations and expectations. A blue planet doesn't have to be friendly. It can be one of the most hostile places imaginable. And yet, from a distance, from the safety of our telescopes and our observations, we can appreciate that blue. We can marvel at it. We can wonder what it would look like to watch those clouds swirl and churn, to see the light scatter through the silicate haze, to witness storms that dwarf any hurricane Earth has ever known. And then there's the question of why HD 189733b has such extreme weather in the first place. The tidal locking creates the temperature difference, yes, but the magnitude of the winds suggests something more complex is happening. There must be intricate patterns of circulation in the atmosphere, jet streams that carry heat from the day side to the night side, convection currents that rise and fall, pressure systems that form and dissolve. The planet's atmosphere is a dynamic system, constantly changing, constantly adjusting to the relentless input of energy from the star. It's a laboratory for atmospheric dynamics, a place where we can test our theories about how atmospheres behave under extreme conditions. And what we learn from HD 189733b might help us understand other planets, both in our solar system and beyond. The physics of atmospheric circulation doesn't care whether a planet is habitable or hostile. The same principles apply everywhere, and by studying the extremes, we gain insight into the whole range of possibilities. Now, shift your thoughts to 55 Cancri E, that world of fire and shadow, of dayside lava oceans and nightside frozen rock. The transition zone between those two regions must be fascinating, a place where the temperature gradient is so steep that the environment changes dramatically over relatively short distances. Imagine walking, if such a thing were possible, from the frozen night side toward the scorching day side. At first, you'd be in total darkness, the sky black and starless, the ground beneath your feet cold, hard rock. As you moved forward, you'd begin to see a glow on the horizon, faint at first, then brighter. The light of the star rising like a permanent dawn. The temperature would start to climb. The rock beneath you would become warmer, then hot, then too hot to touch. You'd reach a point where the ground begins to soften, where the solid rock transitions to a semi-solid slush, and then to fully molten lava. And if you could continue forward, you'd find yourself wading through an ocean of liquid stone, glowing orange and red, with waves of lava rolling slowly past you, viscous and heavy. But you wouldn't make it that far, of course. The heat would overwhelm you long before you reached the molten zone. And even if you had perfect protection from the heat, the atmosphere itself would be toxic, filled with gases bubbling up from the lava, gases that would choke and burn. The sky would be thick with clouds of vaporized rock, creating a haze that scatters the starlight into strange colors. And above it all, the star would hang motionless in the sky, never moving, never setting, a constant source of light and heat that defines the entire day side. On the night side, the star would never rise. It would always be hidden below the horizon, a source of light that exists somewhere beyond reach, illuminating the day side, but leaving the night side in perpetual shadow. And yet, the night side isn't completely cold. Heat conducts through the planet's interior, carried by convection currents in the mantle, warming the night side just enough to prevent it from freezing completely. There's a slow, steady flow of heat from the day side to the night side, a transfer of energy that keeps the planet in a kind of thermal equilibrium. And what about that atmosphere? That secondary atmosphere being continuously replenished by the lava ocean. It's a dynamic system, one where the atmosphere is both created and destroyed on an ongoing basis. Gases bubble up from the lava, adding mass to the atmosphere, while radiation from the star strips away the upper layers, removing mass. The atmosphere is constantly being renewed, a cycle of birth and erosion that has likely been ongoing for the planet's entire existence. This process raises interesting questions about the long-term evolution of planets like 55 Cancri e. How much mass has the planet lost over its lifetime? How has its composition changed as the lighter elements are preferentially stripped away, leaving behind the heavier ones? Is the planet shrinking, growing, or staying roughly the same size? These are questions that future observations might help us answer, as we watch this world evolve in real time. Then, there are the rogue planets, those lonely wanderers drifting through the void. Let's spend more time with them, because they represent something profound about the nature of existence in the universe. A rogue planet is, in many ways, the ultimate exile. It has no sun to warm it, no star to orbit, no solar system to call home. It's alone, truly alone, in a way that's difficult for us to comprehend. And yet, these planets continue to exist. They don't simply vanish because they've lost their star. They persist, traveling through the galaxy on their own trajectories, following paths determined by ancient encounters, by the gravitational influences of stars they pass, by the slow evolution of the galaxy itself. The temperature on a rogue planet would be unimaginably cold. Without a star to provide warmth, the planet cools by radiating away its internal heat, and over time, it approaches the temperature of the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. That temperature is about -455 degrees Fahrenheit, just a few degrees above absolute zero. At that temperature, everything freezes. Any atmosphere that once existed would have long since condensed and fallen as snow, coating the surface in layers of frozen nitrogen, oxygen, carbon dioxide, or whatever gases the planet once had. Water, if there ever was any on the surface, would be solid ice, harder than steel. Even methane and ammonia, gases that remain liquid at much lower temperatures than water, would freeze solid. And yet, despite the cold, a rogue planet isn't necessarily lifeless forever. Deep inside, the planet's core would still be warm, heated by radioactive decay, by the slow release of energy from elements like uranium, thorium, and potassium. This heat would take billions of years to dissipate completely, and during that time, it could maintain a warm interior, perhaps even a subsurface ocean, insulated from the cold surface by kilometers of ice. This is the same principle that keeps Europa and Enceladus warm in our own solar system, allowing them to have liquid water oceans beneath their icy crusts. And if a rogue planet could maintain such an ocean, then perhaps, just perhaps, life could exist there, sustained by chemical energy rather than sunlight, thriving in the darkness beneath the ice. There's also the possibility that rogue planets could have auroras, faint glows in the sky caused by interactions between the planet's magnetic field and charged particles in interstellar space. These auroras wouldn't be as bright as Earth's northern lights, but they would be visible, creating ghostly curtains of light that dance above the frozen surface. In the absence of any other light source, these auroras might be the only illumination on a rogue planet, the only break in the eternal darkness. And if there were anyone there to see them, if there were life forms adapted to the cold and the dark, those auroras would be their stars, their constellations, the only patterns in the sky to mark the passage of time. Rogue planets also pass through interstellar space, which isn't completely empty. There are clouds of gas and dust scattered throughout the galaxy, regions where new stars are forming, nebulae glowing with the light of young stars. A rogue planet might drift through one of these clouds, and for a time, it would experience something like an atmosphere again, a thin shell of gas and dust surrounding it as it moves through the denser medium. That atmosphere would be temporary, lasting only as long as the planet remained in the cloud. But it would create a brief moment of change, a fleeting experience of something other than the cold emptiness of interstellar space. And then, the planet would emerge from the cloud, back into the void, and the temporary atmosphere would disperse, leaving the planet alone once more. There's something melancholic about rogue planets, but also something hopeful. They remind us that being alone doesn't mean being worthless, that a planet without a star still has value, still has a story. And in the vastness of the galaxy, these lonely worlds outnumber the planets that orbit stars. They're the majority, not the exception. And that changes our perspective on what it means to be a planet. It means that planets don't need stars to exist. They don't need warmth or light or a central anchor. They can exist on their own terms, following their own paths, carrying their own histories forward into the future. Now let's revisit Kepler 16b, that circumbinary planet with two suns. The mechanics of orbiting two stars are more complex than orbiting just one, and it's worth taking a moment to appreciate the elegance of this system. The two stars orbit each other closely, bound by gravity, locked in a mutual dance. And Kepler 16b orbits around both of them, following a path that encircles the binary pair. This isn't an unstable arrangement, as you might think. In fact, it's quite stable, as long as the planet orbits far enough from the stars that their combined gravitational influence acts more or less like a single central mass. Too close, and the planet would be pulled in different directions by each star. Its orbit would become chaotic, and it might eventually be ejected from the system. But at the right distance, the forces balance out, and the planet can orbit peacefully for billions of years. The view from Kepler 16b would change dramatically depending on where the planet is in its orbit. When it's on one side of the stars, both suns would be in the sky together, close to each other, their light mingling to create a warm orange glow. As the planet moves around its orbit, the angle between the stars would change from its perspective, and they would appear to separate, moving apart in the sky until they're on opposite sides. And then, as the planet continues its orbit, the stars would come back together again, converging until they're side by side once more. This would create a complex pattern of daylight, where the intensity and color of the light changes constantly, where shadows shift and dance in unpredictable ways, where the concept of a day becomes more nuanced than simply the time it takes for the sun to rise and set. And imagine the eclipses. From Kepler 16b's perspective, the two stars would regularly eclipse each other, one passing in front of the other, blocking its light. These eclipses would happen every 41 days, as the stars complete their mutual orbit. And during each eclipse, the amount of light reaching the planet would drop noticeably. If you were standing on Kepler 16b, if that were possible, you'd see one sun slowly move in front of the other, the light dimming as the smaller sun is swallowed by the larger one, until only a partial ring remains. And then, gradually, the smaller sun would emerge from behind the larger one, and the light would return to its full brightness. These eclipses would be predictable, regular, a rhythm that marks the passage of time in the system. Kepler-16b also raises interesting questions about habitability in binary star systems. While this particular planet is too cold and too gaseous to support life, there's no reason why an Earth-like planet couldn't exist in a similar system, orbiting two stars at a greater distance, in the habitable zone where temperatures are right for liquid water. If such a planet existed, life there would evolve under a very different set of conditions than life on Earth. The changing patterns of daylight, the eclipses, the varying intensity of radiation, all of these factors would shape the evolution of any organisms that arose. Perhaps life would develop strategies for dealing with the changing light levels, like plants that adjust their photosynthesis based on which suns are visible, or animals that navigate using the positions of both stars. Perhaps intelligent life would develop a culture deeply influenced by the double suns, with myths and stories that revolve around the binary nature of their celestial parents. And then there's WASP-12b, that doomed planet spiraling into its star. This world offers a glimpse into the eventual fate of many hot Jupiters, and perhaps even some planets in our own solar system, billions of years in the future. Tidal forces are relentless. They don't care about the planet's history or its potential. They simply follow the laws of physics, transferring energy from the planet's orbit into heat, causing the orbit to decay. And as the orbit shrinks, the planet gets closer to the star. The tidal forces become stronger, and the decay accelerates. It's a feedback loop, a death spiral, and there's no way to stop it. WASP-12b is caught in this spiral, and there's nothing that can save it. But before it vanishes completely, WASP-12b will leave a legacy. The gas that's being stripped from its atmosphere, the material that's flowing out into space and spiraling into the star, that matter will be recycled. It will become part of the star, adding to its mass, enriching it with heavier elements. And when the star eventually ends its own life, billions of years from now, some of that material will be expelled into space, scattered by stellar winds or supernova explosions, and it will become part of new clouds of gas and dust, new star-forming regions, new generations of stars and planets. In this way, WASP-12b's matter will persist even after the planet itself is gone. It will be reborn, transformed, woven into the fabric of future worlds. Nothing is ever truly lost in the universe. It's just changed, recycled, given new form. The shape of WASP-12b, that egg-like prolate form, is also worth contemplating. It's a reminder that planets aren't always spheres. We're used to thinking of planets as round, because gravity tends to pull matter into spherical shapes. But when external forces are strong enough, they can distort that shape. The tidal forces from the star pull on WASP-12b's near side more strongly than its far side, creating a bulge, stretching the planet toward the star. And as the planet rotates, this bulge tries to align with the tidal force, creating friction, generating heat, and contributing to the planet's inflation. It's a complex interplay of forces, one that's slowly tearing the planet apart, while also making it larger and more vulnerable to further stripping. As for GJ436b and its hot ice, this planet represents a frontier in our understanding of matter. The high-pressure phases of water ice are relatively well understood in laboratory settings, where scientists can create the necessary conditions and study the properties of these exotic ices. But seeing them in a planetary context, observing them in the wild, so to speak, is something new. It confirms that our theoretical models are correct, that the physics we've worked out in the lab applies on a planetary scale. And it opens up new questions about the interiors of super-Earths and mini-Neptunes, many of which might have similar compositions. How common are these hot ice worlds? Do they represent a large fraction of the exoplanets we've discovered? And if so, what does that tell us about the distribution of water in the universe? Water is everywhere in the cosmos. It's one of the most common molecules, formed from hydrogen and oxygen, two of the most abundant elements. But the form that water takes, whether it's a gas, a liquid, a solid, or one of these exotic high-pressure phases, depends on the local conditions. On Earth, we're familiar with water in all three common states: ice, liquid water, and steam. But in the universe as a whole, water exists in many more forms, each one suited to its environment. And GJ 436b shows us that even in places we wouldn't expect to find ice, frozen water can exist, preserved by the crushing pressure of the planet's gravity. Kepler 78b, the silent planet, challenges us to imagine a world without sound, without weather, without the dynamic processes we take for granted. Its surface is molten lava, yes, but that lava doesn't flow like water. It's thick, viscous, moving slowly, more like honey than like a river. And without an atmosphere to create winds or storms, the surface would be eerily still, disturbed only by the slow churning of the lava itself and the occasional impact of a meteorite. Though even those impacts would be silent, the sound swallowed by the vacuum. The planet's proximity to its star also means it's tidally locked, with one side always facing the star and the other always in darkness. The day side would be a sea of glowing lava, radiating heat into space, while the night side would cool slightly, perhaps solidifying in places, though it would never get cold enough to form a stable crust. The idea of a silent world is both peaceful and unsettling. On Earth, we're surrounded by sound. Even in the quietest places, there's always something: the rustle of leaves, the hum of distant traffic, the sound of our own breathing. But on Kepler 78b, there would be nothing. No wind, no waves, no birds, no insects, just silence. And that silence would be absolute, not the quiet of a soundproofed room, but the absence of any medium for sound to travel through. It's a kind of silence that doesn't exist anywhere on Earth, and it's difficult to even imagine. But perhaps, in that silence, there's a lesson. That sometimes the most powerful presence is absence. That in the void, there's a kind of clarity, a stripping away of all distraction, leaving only the essential. Finally, let's return to TRES 2b, the darkest planet. This world absorbs light with an efficiency that's almost unnerving. It's as if the planet is a shadow given form, a void in space that refuses to reflect. And yet, it's not completely black. It glows, not with reflected light, but with its own heat, emitting infrared radiation that makes it visible to our instruments. In a way, TRES 2b is like a coal in a fire, dark but warm, absorbing the light of its star and converting it into heat, then radiating that heat back into space. The atmosphere of TRES 2b likely contains complex molecules, hazes of organic compounds that form when simpler molecules are broken apart by the star's radiation and then recombine into more complex structures. These molecules absorb light across a wide range of wavelengths, preventing it from being reflected. It's similar to the process that creates smog on Earth, where pollution particles absorb and scatter light, reducing visibility and darkening the sky. But on TRES 2b, this process happens naturally, driven by the intense heat and radiation, creating an atmosphere that's more opaque than any polluted sky on Earth. There's also the possibility that the planet's darkness is influenced by its magnetic field. Hot Jupiters, like TRES 2b, are thought to have strong magnetic fields, generated by the motion of conducting material in their interiors. These magnetic fields can interact with the atmosphere, affecting the distribution of particles, creating charged regions where chemical reactions occur more readily. If the magnetic field is strong enough, it could create belts or zones in the atmosphere where light-absorbing compounds are concentrated, making the planet even darker. This is still speculative, but it's an intriguing possibility that future observations might test. And as we study TRES 2b more closely, we're learning not just about this one planet, but about the general properties of hot Jupiters, about how their atmospheres behave, about what makes some of them bright and others dark. Each planet is a data point, a piece of a larger puzzle, and together, they're helping us build a comprehensive picture of planetary diversity in the universe. As you settle into sleep tonight, let your mind wander among these worlds. Picture yourself floating above HD 189733b, watching the blue storms rage below. Imagine standing at the edge of 55 Cancri E's lava ocean, feeling the heat radiating from the molten rock. Drift through the cold darkness alongside a rogue planet, silent and alone. Watch the double suns of Kepler-16b set together on the horizon. Stand on WASP-12b as it slowly unravels, its atmosphere streaming away into space. Touch the hot ice of GJ-436b, solid despite its heat. Listen to the silence of Kepler-78b, where no sound can travel, and gaze into the darkness of TRES 2b, the blackest planet in the universe. Each of these worlds is real. Each one exists somewhere in our galaxy, orbiting a distant star, following its own path through the cosmos. And each one is a reminder that the universe is far stranger, far more creative, far more wonderful than we ever dared to imagine. You have done enough for today. The universe will still be here tomorrow, with all its mysteries and wonders, waiting patiently for us to explore them. Close your eyes now, rest your mind, and let yourself drift among the stars. Dream of planets where glass falls like rain, where oceans glow with molten rock, where two suns hang in alien skies. Dream of worlds we haven't yet discovered, of possibilities we haven't yet imagined. And know that out there, somewhere in the vast darkness, those worlds are real. They're spinning quietly around their stars, following ancient orbits, carrying their strange stories forward into the future. And one day, perhaps, we'll visit them. But for now, let them visit you. Let them fill your dreams with their impossible beauty, their quiet strangeness, their endless wonder. Good night, dear traveler. May your dreams be as strange and beautiful as the planets we've explored together. And may you wake tomorrow with a sense of awe at the universe we call home, a place where even the strangest things are possible, where mystery and wonder are always just a telescope away. From the Sleepy Library, sleep well.